Okay, I'm continuing from the last video. I was having trouble with the focus, but let's keep going. So I'm looking at the gradient of a tangent line, which, if you remember, is the gradient of the line that goes through a point on the curve and has the gradient of the curve at that point. So in this example, I'm looking at the function f of x equals 2x to the power of 4 plus 3x squared minus 2, and I'm looking at that at the point 1, 3. Now the point 1, 3 is on the curve. If I substitute x equals 1, I get 2 times 1 plus 3 times 1 minus 2, which does give me y equals 3 at that point. All right, so I need to find the gradient of the tangent line to the curve. In other words, I need to find the derivative in order to find the gradient. The derivative function tells me the gradient of the function at that point. So what I need to find then, is f dash of 1, basically. Now first I need to find f dash of x. So f dash of x, I multiply these numbers together, 4 times 2 to get 8x. I subtract 1 from the power, 8x cubed, plus 3 times 2 gives me 6x, subtract 1 from the power, that's 1. So 8x cubed plus 6x. I've got a constant on the end, so there will be no third term in the derivative. Okay, now I can find f dash of 1. That's going to be 8 plus 6, which is going to give me 14. Done. Okay, that's the gradient. All right, now I'm going to talk a little bit about notation. Is that in focus? Oh, I think it's okay. So there are 3 different ways that we can write the notation when we're finding derivative. And one of the things you need to be able to do is identify which kind to use. You don't need to know so much about the history or why there are 3 different kinds. There are kind of 2 different kinds historically, but there's a third way of writing the derivative. You need to know which kind to use. So the first one is called Leibniz notation. It's named after the mathematician Leibniz. Basically, what you do here is, instead of having f of x, if you've got an equation with a y in front, y equals x squared, then you use this notation, and we call it dy dx, and dy dx equals 2x when y equals x squared. So if you're asked to find the derivative of y equals x squared, your answer would look like that. All right. Now, the dy and the dx mean a small change in y and a small change in x. All right. That's really all you need to know. It's not d times y and d times x. All right. If I go to the second kind of notation, try and get that light out. There we go. The second kind of notation is named after another mathematician called Lagrange. That really doesn't matter. When I have function notation, f of x equals x squared, then the derivative of the function, I'm going to use f dash of x notation. Okay, so if the question is given to me here, find the derivative of this function, then I'm going to write my answer using f dash of x. Now the third kind I'm going to call operator notation, and I call it operator because it's finding the derivative is an operation. It's something I can do to an expression. So if I'm given an expression like x squared instead of an equation, then what can I do to this expression? Well, I can multiply it, I can add it, I can subtract it, or I can find its derivative. So d dx of x squared is how I read that out, equals 2x. And the instruction might be, in words, differentiate with respect to x. That's how I would read that. I would either read d dx of x squared, or I would read differentiate with respect to x. So here are some examples just to demonstrate what I'm going to do differently each time. So in the first one, this is going to be my Leibniz notation. So y equals 4x squared minus 2x plus 1. I'm going to use dy dx equals 8x minus 2. Okay, so I found the derivative. If I want to find the derivative for f of x equals 7x to the power of 5, I'm going to use my Lagrange notation. F dash of x equals 7 5s are 35. Take 1 from the power. 35x to the power of 4. In the last example, the question is 2x cubed minus x squared. So I'm given an expression, not an equation. So it asks me to find the derivative. I can't just write equals underneath because it doesn't equal its own derivative. So I'm going to write d dx of 2x cubed minus x squared equals, what is the derivative? It's 6x squared minus 2x. Okay, 3 more examples. I'll work through them quickly. For this example, the easiest thing to do here is first to expand. So I'm going to get t squared minus 2t plus 1. That's y. So I need dy dx, because I'm starting with y, equals 2t minus 2. In the second example, I can see that I have a common factor of t, so I need to simplify before I can derive. If I simplify that, I'm going to get 3t squared minus 1. So f dash of t is going to be 6t, because I multiply the 3 times the 2 and I subtract 1 from the power. The minus 1 is going to give me a derivative of 0. The last one, x cubed over 5, is an expression, so I'm going to write d dz, so make sure you use the right variable, of z cubed over 5 is going to be 3 times, and dividing by 5, z squared. Let's keep going. Example 4. Now I'm going to, okay, this is a slightly different kind of example. Find the coordinates of the points on the curve with this equation, y equals x cubed plus 6, at which the gradient of the tangent line is 12. Now notice here, it's point with an s in brackets. The question is not giving away whether there is one or more point that has this equation, this gradient. Okay, so I need to do my work and I'll soon see how many solutions there are. But basically what it's telling me is the gradient is 12 at the point I'm looking for. So I'm dealing with gradient, I'm going to need to find the derivative. dy dx of this equation, y equals x cubed plus 6, is going to be 2x squared. And I know that the derivative is 12. So therefore I know that 2x squared equals 12. 3x squared. It's 3. It's definitely 3. 3x squared equals 12, which gives me x squared equals 4, which gives me 2 possible solutions, x equals plus or minus 2. Always remember that when you have an even power and you're looking for an unknown, there's going to be 2 solutions, plus and minus. Okay, so x can be positive 2, x can be negative 2. I'm tempted to move on. Go back and check what the question says. Find the coordinates of the points. Remember, you never move on from a question without first going back and rereading the question. I actually need to find the 2 points. So one is going to have x is negative 2 and the other one is going to have x is 2. So if I put negative 2 into this equation, I get negative 2 cubed plus 6. That's negative 8 plus 6. That's going to give me negative 2. Yep. And the next one is 2 cubed plus 6, which is going to give me 8 plus 6, which is going to give me 14. So I found the 2 points. All right. How long is this? Well, let's keep going a little bit longer. So now I'm looking for the angle of the tangent at a point. Now, we did briefly meet this last year, but let's go over it again. It's not tricky. When you have a tangent line, and so this tangent line in this diagram, for example, might be the tangent of a curve, let's say here at this point. So I've done some work to find the tangent line. Now the question is, what angle does this line make with the x-axis? Because it's a line, it's going to go on forever. It's eventually going to meet the x-axis unless it's horizontal. So when it does meet the x-axis, what will the angle be? And the only thing you really need to remember is that this angle is always measured from the positive direction of the x-axis in an anti-clockwise direction. So that doesn't matter whether my line has a positive or a negative gradient. If it's a positive gradient, it's going to give me an answer somewhere between 0 and 90. If it's got a negative gradient, it's going to give me an answer somewhere between 90 and 180. And the equation I use is m, that is the gradient, equals tan alpha. but we find the gradient by using the derivative. So here's an example. Example 5, find the angle that the tangent line of this function f of x equals x squared minus 3x plus 5 at the point 1, 3 makes with the x-axis. Double check this point 1. Yes, that's going to give me 1, 3. Okay. So what do I need to do here? I'm looking for the tangent line. I need the gradient of the tangent line, and that's given to me by the derivative. So I need to find f dash of x, and eventually I'm going to need f dash of 1. I need to know what the gradient is when when x equals 1. So first I find f dash of x. That 2 becomes a constant out the front, 2x minus 3, because that 1 times that minus 3 becomes negative 3. This power will become 0. It'll be x to the power of 0, which is 1. So f dash of x equals 2x minus 3. F dash of 1 then is going to be 2 times 1 minus 3, which is negative 1. Okay. So I'm going to use the equation which is on the previous page, which is this, m equals tan alpha, where alpha is the angle I'm looking for. The gradient I've just found, it's negative 1. Okay, and this is going to give me alpha equals 135 degrees. If you need to review what happens when I'm finding the inverse tan when it equals negative 1, go back and review it. But we are going to be revisiting chapter 6 soon. But that's worth revisiting from last year if you can't remember it. Okay. Oh, and for this one, your answer is always going to be between 0 and 180 because the angle is above the x-axis. So if I go back to my diagram, case 1, positive gradient, it's going to give me an angle of somewhere between 0 and 90, so it's an acute angle. Case 2, I've got a negative gradient, it's going to give me an obtuse angle. It's be one of those two, okay? All right. Can we push on? Yeah, let's finish this. Okay, so increasing and decreasing functions. We have met increasing and decreasing functions, but we need to review it, and we need to look at what the rule is for when a function is strictly increasing or strictly decreasing. So if I have some function and I choose an interval on that function, and I find that everywhere on that interval, if I have 2 points, x1 and x2 is bigger than x1, that means it's to the right along the x-axis. If that implies that f of x2 is greater than f of x1, that's a 2, sorry, that's tiny for you guys, that's a 2 there. F of x2 is greater than f of x1, in other words, the y value is higher for the second point than the first point. That basically means that my graph has done that, okay? Here's x1, f of x1, that's the first point. Here is x2, f of x2, that's the second point. If the second x value is to the right of the first x value and the second y value is above the first y value, then my function has increased. Think of increasing as positive gradient, okay? On the other hand, it's strictly decreasing if x2 is greater than x1, implies f of x2 is less than f of x1. In other words, my 2 points will look like that. Okay, not necessarily on a straight line, but if I have a curve and I pick any 2 points on that curve and I get that this implies that, then my function on that interval is strictly decreasing. Bearing in mind, you can have a graph that's not that, for example, looks like this. I can say, all right, in this section from this turning point to this turning point, over that interval, my graph is decreasing. Now, another thing to note, strictly increasing implies f dash of x is greater than or equal to 0. So we can use derivatives to find when my graph is strictly increasing. This says my gradient is equal to or more than 0, okay? The gradient can be 0. So if I look at this little diagram here, if I sit right on this point here, where my gradient is 0, that's the turning point, and then I choose any other point to the right, then it is true that I've gone to the right and down, therefore it is true that I'm strictly increasing, including this point here. So this point is special because it can be included in both this little section here, which is strictly decreasing, and it can be included in this interval, which is strictly increasing. So the turning points can be in both. And generally speaking, when you're asked to define an interval that is strictly increasing or decreasing, you should find the biggest one possible, which means you should include those endpoints. So, quick example, and then that's the end of this one. Example 6. For the following graph, find an interval when the graph is strictly increasing and an interval when the graph is strictly decreasing. An interval. I don't need to find all of them. However, I should find the biggest one that I can. So, I'm going to start with strictly increasing, and that happens, just change colour, on this section of the graph here. And I know that because I've got 2 turning points and the graph has a positive gradient for that entire section until I meet the turning point. So the answer to A is in between x is -2 and x is 3. Okay. Now I've got 2 options for B. The graph is strictly decreasing. I've got this section here. I've got this section here. Doesn't matter which one I choose. I'll just choose this one. So I'm starting when x is 3 and I'm continuing on now forever because I'm going to assume this graph continues to go down, down, down. All right. If I had chosen this interval over here, it would look like this, -infinity to -2. Oops, sorry, that should be curved. -infinity to -2. Never ever, I'll say this now, never ever leave an answer that looks like this. Is it a square bracket or is it a curved bracket? I'm not sure, right? I am not going to pay that if I'm marking your work. If it looks a bit dodgy, just cross it off and rewrite it to make it really clear what you actually intend to be your final answer. All right, that is us for 9B. That's it.